Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. Today we are beginning a new chapter, that is flow through pipes. So let's begin. Our first topic for today is loss of energies in pipe. So there are two kinds of losses here. First is major energy losses. These major energy losses are primarily due to the friction. So there are two formulas that we are going to discuss here. First is Darcy Wisbech equation. And second is Chase's formula. Chase's equation we can write down. And there are other minor losses. Here we have number of losses. First is sudden expansion. Sudden contraction. Then bend in pipe. Pipe fittings. And the last one is obstruction in pipe. So these are the list of losses that can occur in a pipe. Now we will see the major energy losses. First is A. Darcy Best formula. We have already studied this in our previous chapter. This is just a revision. So here we know HF is equal to 4F L D square 4FL D square upon 2GB, where here HF is equal to head loss due to friction. Then F is the coefficient of friction. And here value of F varies in accordance with the Reynolds number, which is given in this way: 16 upon R. When RE is less than 2000, that is viscous flow. And the next value of F is 0.079 RE raised to 1/4. That is for 4000 less than RE less than 10 raised to 6. So remaining terms are known. L is length of pipe, V is velocity, D is diameter. Now let's move forward to our next equation. That is a little bit new. B is chases formula. So here we have also derived one equation for this in our previous topic or chapter. HF is equal to F prime upon rho G multiplied by P upon A multiplied by L multiplied by V square. Again, HF is the head loss, A is the area, P is the parameter, L is the length. So we will define one term here, that is hydraulic mean time. Which is denoted as M, and it is given by cross-sectional area upon perimeter, or area of flow upon wetted perimeter. And in this case, here we can write down this as pi by 4 d square upon pi d. So here you will be getting this answer as d by 4. And we can put this over here, that is HF is equal to F prime upon rho G multiplied by 1 upon M multiplied by L multiplied by V square. So here we can get the value of V square is equal to HF multiplied by rho G upon F prime multiplied by M multiplied by 1 over L. So we can rearrange the terms. Rho G upon F prime multiplied by M multiplied by HF upon L. So here the value of V can be written as square root of rho G upon F prime square root of M into HF upon L. Now we will be considering square root of rho G upon F prime as a constant C. And one more thing here, square root of M into I. Now what is this? First of all, let me write down here that C is equal to J is constant I is equal to HF upon L that is equal to loss of head per unit length. So that that is the way we can obtain the velocity. So let's copy this work into our new slides. Our next theory is about minor energy losses. So our first loss is due to sudden enlargement. Loss of head due to sudden enlargement. So we have a ready-made figure. So here, let's continue. So there are few nomenclatures that we will not discuss much in detail. That here we have P1, that is pressure intensity at section 1, V1, that is velocity value at section 1, A1 is the area at section 1. Similarly, we will have values P2, V2 and A2. Now what happens here, that there is a sudden enlargement. So because of this sudden enlargement, the fluid in the pipe is not able to follow this sudden enlargement. So because of that, there will be some eddy formation that can be observed over here and energy losses takes place. So let us say P prime is equal to pressure intensity of liquid eddies on the area A2 minus A1. Then HE is equal to loss of head to sudden enlargement. Now applying the Bernoulli's equation, P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus HE. So here the value of HE can be written as P1 upon rho g P1 upon rho g minus P2 upon rho g plus V1 square upon 2g minus V2 square upon 2g. Z1 and Z2 are cancelled because they are at the same height. So we will leave this head loss over here and discuss slightly different thing. Here, if you see the figure over here, in this figure there is a pressure force P1A1 on section 1, pressure force P2A2 on section 2, and there will be a force due to the turbulent eddies. So the net force in x direction is given by Fx is equal to P1 A1 plus P prime. P prime we have written pressure intensity of liquid eddies on area A2 minus A1 minus A1 minus P2 P3. Here, okay, now we can continue from here. But experimentally it is found that P prime is equal to P1. So once we put that over here in Fx, we will get P1 A1 plus P prime. Okay, so we are going here P1 A2 minus A1 minus P2 A2. So here finally what we will be getting here is P1 minus P2 into K2, that will be the value of Fx. Now we will discuss something about the momentum. Momentum of liquid at section 1, 1. So here it will be mass into velocity. So it will be rho A1 V1 multiplied by V1. So it will be equal to rho A1 V1 square, and then we can write down momentum of liquid at section 2. So here it will be equal to rho A2 square. So the change of momentum per second is equal to rho A2 V2 square minus rho A1 V1 square. Now from continuity equation, A1 V1 is equal to A2 V2. So we can say the value of A1 is equal to A2 VT upon V1. So here change in momentum per second can be modified now is equal to square minus rho A2 V2 upon V1 into V1 square. So the change of momentum we are getting is rho A2 into the bracket V2 square minus V1 V2. So let's copy this work into our main slides. So that is the end of this lecture. Thank you for watching this video.